Hello and welcome to this video, the first in a two-part series introducing the Hodge star operator. So let's make a start then. So the Hodge star operator is a central concept in differential geometry and mathematical physics, particularly in the study of manifolds and exterior calculus. It provides a way to relate different forms on a manifold and is crucial in formulating theories such as electromagnetism in a coordinate-free manner. Now, in this introduction, we'll explore the definition, properties, alongside some detailed examples to illustrate its usage. So let's make a start. So this is part one, and the video that follows up this will be part two. All right, now, perhaps here. So by transforming a K form into its complementary n minus K form, now n is the dimension of the space, and K is the degree of the form. The Hodge star operator gives us a more concrete, complete understanding of the geometric and physical structure of the space we are working with. So let's have a look at the definition here. So the Hodge star operator is a linear operator that acts on differential forms on a manifold. Specifically, it is an isomorphism between the space of K forms and n minus K forms on an n-dimensional oriented Riemannian manifold, MG. M manifold G the metric, where G is the metric tensor. Now, mathematically, the Hodge star operator is denoted by the star and is defined as the star is a mapping from the space of K forms on the dual tangent space or cotangent space to the space of n minus K forms on the same dual tangent space. So, where lambda K, capital lambda K, of the dual or cotangent space is the space of K forms on M. All right, now I might hide that. All right, now let's move on then. So let's begin by looking at how the Hodge star works in R. I'll go for an introduction and then I'll pick up some definitions after this. All right, so now let's have a look in the reals, one dimension. All right, in one dimension, there's really only two basic K forms. And when I say basic, I mean without constants, I mean just the most basic form you can get. So in one dimension to consider, there's only two, the zero form 1, it's the simplest of all, the number 1, and the 1 form dx, no constants in front except for the constant 1, dx. So they're the simplest two you can have. And it turns out that they're the only two basic ones that you can have. All right, so one wedge Hodge star of 1 equal to dx implies that the Hodge star of the zero form 1 is dx, and dx wedge Hodge star dx is just dx, implies that Hodge star dx is 1. Okay, now what you're going to find is on the right here, in all these cases, the volume form for that dimension goes here. It's the highest form you can have. Right, so one dimension you have dx. Now, I mean, you could have a constant, some scalar times dx, but we're just picking the basic ones here. So let's now move on and have a look at R2, two dimension. Now here we're only in Euclidean space, hence R2, Euclidean space. Now the basic form here, the basic forms here are the zero form, 1, and the 1 forms dx and dy, and the 2 form dx wedge dy. All right, so they're all your basic forms in R2, all right, or two-dimensional Euclidean space. All right, so let's go through the same process we did above. There'll just be a couple more calculations involved, but 1 wedge star 1 or Hodge star 1 is dx equal to dx wedge dy. Well, that implies that the Hodge star of 1, the zero form, is dx wedge dy. Now, dx wedge dy, the 2 form, wedged with the Hodge star of that 2 form, dx wedge dy, is dx wedge dy, implies that the Hodge star of the 2 form, dx wedge dy, is 1, because this wedged with 1 gives us this. Keep going. So we have over here dx wedge Hodge star of dx is equal to dx wedge dy. Well, that implies the Hodge star of dx is dy. And then just watch with the next one carefully. The wedge, dy, wedge Hodge star dy, or star dy, is equal to dx wedge dy, well, that implies that the Hodge star of dy must be minus dx. And why? Because if I put minus dx in here, then dy wedge minus dx is equal to dx wedge dy, because by flipping, these being anti-symmetric, I then become dx wedge dy. Okay, so by putting the dx in the second place here, okay, to make it equal to that, I need to put a minus sign there. Okay, so there's the Hodge stars in R2. And we'll just take it one more day. Let's have a look at how it works in R3. Okay, so 1 wedge star 1 is equal to the volume form in R3, dx wedge dy wedge dz. Well, that implies that Hodge star 1 or star 1 is dx wedge dy wedge dz. Okay, let's take the volume form itself and wedge it with its Hodge star. Right, it's dual, Hodge star dual. Set that equal to the volume form in that space, then clearly star of the volume form must be 1. Dx wedge star dx equal to the volume form. Star dx implies dy dz. If you notice here, if I replace Hodge star dx with dy wedge dz, then dx wedge dy wedge dz perfectly agrees with the volume form. Okay. That's how they work. Always put the volume form on the right here, and you'll be able to work out what the Hodge star is. That's the point of these examples here. Dy wedge star dy is equal to the volume form, so that implies that star dy is dz wedge dx. Okay, funny order there. If you put that dz wedge dx in here, so you have dy wedge dz wedge dx, and if you move that 2 spaces, you move the dx 2 spaces, you'll end up with a positive coefficient in front again, and you'll have the volume form. Dz wedge star dz equal to the volume form implies that star dz is equal to dx wedge dy. Simply if you put dx wedge dy in there, you'll see that that works as well. And 2 moves of the dz will give you the required volume form. Let's keep going now. Dy wedge dz, wedge with the star of dy wedge dz equal to the volume form implies star is dy wedge dz is dx. Down here, dx wedge dy, wedge with the star, Hodge star of dx wedge dy equal to volume form implies that the Hodge star of dx wedge dy, this bit here, is equal to dz. If I substitute dz in there, I get the volume form. Dz wedge dx, wedge with the star of dz wedge dx is equal to volume form implies that the star of dz wedge dx is dy. Again, if I put dy in there, and then I can make some moves, you'll find I'll end up with the volume form. In fact, if I take this dz here and I move it twice, I'll end up getting the volume form here. So that's how they work. All right, so let's look at the construction of the Hodge star operator. So to construct the Hodge star operator, we begin with an oriented Riemannian manifold, Mg, of dimension n and a k-form omega. Okay, G is the metric, of course. The Hodge star operator maps omega to an n minus k form called star omega or Hodge star omega, such that omega wedged with the Hodge star of eta is this inner product times the volume form. Now, in the previous couple of examples, 3 of them, we used coefficients. Our constants were 1 in all of them. So this would just equal 1, but you'll see it equals more. These are the constants that go in front of our k-forms. Now, for all eta belong to the space of k-forms on the dual or cotangent space of the manifold, all right? Where this is the inner product on forms induced by the metric G. I'll give some examples of that. And volume subscript M is the volume form on M. M might be just R3 or R4 or some Euclidean space. It might be some other Riemannian manifold. It's just depends on what the case is. So now, and that's defined by the volume subscript M, the volume form on the manifold there, is the square root of the determinant of the metric, and then this wedge product dx1 all the way up to dxn, where n is the dimension of the space you're in. Mod G here is the determinant of the metric tensor. Now, orientation, by that, we up here, oriented Riemannian manifold, just a consistent choice of direction across the entire manifold, allowing you to distinguish between clockwise and counterclockwise, or more generally, the positive and negative orientations in higher dimensions. All right, so the consistent choice of direction is what we mean by oriented. All right, which is important because direction matters when we're dealing with these forms. All right, so metric dependence. The Hodge star operator is heavily dependent on the metric G of the manifold because it involves an inner product to define the complementary form. Remember how we go from the K form to the n minus K form? The metric plays a role in doing that. All right. This next example, I'm going to use the Euclidean metric, but in special relativity, you'd have the Minkowski metric, and then in general relativity, you again got the metric with varying components. All right, now this dependence is crucial as it ensures that the transformation respects the geometric properties of the manifold. So let our manifold be R3, so three-dimensional Euclidean space, just to keep things simple at the moment, just to communicate the idea. And given the following two forms, omega is, the following two one forms, each is a one form, my apologies, each is a one form. All right, and given the following two one forms, omega is a dx plus b dy plus c dz, a, b, and c are constants. All right, and so when we write this as a row vector, a covector with a, comma, b, comma, c, comma, b, c, b, comma, c, it's assumed or implied that dx is in there, dy, dz. Okay, we don't need to explicitly write them. We understand that they are there. Okay. Now, eta is f dx plus g dy plus h dz. F, g, and h are all scalars. They could be numbers, they could be functions, same as ABC here. Could be numbers, they could be functions or variables, but they're scalar quantities. Okay, the basis one forms are implied here, as I've just pointed out. So the inner product here, denoted by the angled brackets, omega, comma, eta, is this object here. Okay, and to evaluate that, we have the row vector, we have the metric here. Now, in the Euclidean metric, it's just Euclidean metric in 3 dimensions. It's just the diagonal matrix here with ones in the diagonal and zeros everywhere else. In special relativity, Minkowski space would be in R3 plus 1, and so we would have minus 1 here, 1, 1, another 1 down here, and everything else 0. Okay, and that's how you conduct the inner product. So just be aware, this is the metric here. Transpose of the other row covector, row vector, transpose here. And so when we do that, we get this, and we perform this product here, this contraction here, inner product, and we end up with AF plus BK plus CH. So all of this is a scalar. Scalars multiplied together and then summed. Okay, so that's what we have. Let's keep going. Now, local coordinates. So in local coordinates, so in the local coordinate patch, some open set U, local coordinate patch, a K-form omega can be expressed as omega is this here, the sum sigma, the components here, and then the basis one forms wedged together, okay, up to the value of K. It's a K form. So a 2 form will go up to 2, a 3 form will go up to 3, 3 of these basis vectors. A 4 form will have 4 of these basis vectors wedged together. All right. N is like the dimension of the space. All right. And the Hodge star of omega, that star omega, is then given by this convenient rule here. Square root of the determinant of the metric, n minus k. This is a factor to normalize it, as I was talking about with the wedge product in the last video prior to this. And then we have the sum over the I and the j. Okay, now this is the Levi-Civita symbol here, and I'll talk about that shortly, but it deals with the permutations of these indices here. So this is the Levi-Civita symbol, and the symbol is over n minus k tuples. Okay, here we go, J1 to J, because remember, k is the degree of the form, n minus k is the degree of the Hodge star form. Okay, the dual form, if you like, it's dual to omega. So this is dual to this omega, a sort of dual. Okay, now Okay, so let's do an example of all this. So example, let's calculate the Hodge star of a two form in R4, four-dimensional Euclidean space, with the standard Euclidean metric where the determinant, what G, is 1. All right, now, so we let omega equal A dx wedge dy plus B dz wedge dw. A and B are constants, be a two form in R4. And we want to find star omega, the Hodge star of omega. So, okay, step one. Let's identify the components. Now here, omega is a two form, so k equals 2, degree of the form, and we're in 4 dimensions. Yep, 4-dimensional, Euclidean 4-dimensional space, so n is 4. And the components, omega ij, okay, correspond to the coefficients of the two forms. So omega 1, 2 is A. Why 1, 2? Because x is the first variable, y is the second variable, z is the third variable, w is the fourth variable coordinate. Okay, so x, y, z, w are the coordinates in this space, in this 4-dimensional space. X is 1, y is 2, z is 3, w is 4. So w1, 2 is A, w3, 4 is B. All right, so w1, 2 here, w3, 4 here. Okay, now, so the formula for the Hodge star in this case becomes star omega, square root of the determinant of the metric, which will just be that diagonal matrix, n minus k factorial, and then sigma from 1 to 4, okay? And now we have here 4 dimensions. We have here now the Levi-Civita symbol, and we're going to have 4 elements up here now, because there's 4 combinations, there's 4 coordinates, and there's 4 permutations of those coordinates. And then omega I1, 2, I1, I2, which we'll deal first off with this one in a minute on the next slide. dxj1, wedge dxj2. Okay, so we can put that in there. Here we can put in, well, n and k we can put in 4 and 2. All right, and over the next page we'll deal with the next bit. All right, so omega star becomes 1 on 2 factorial, sigma over all of this. Now let's apply the Levi-Civita symbol. Let's deal with that next. We have 2 non-zero components of omega, so we'll calculate their contributions separately. Remember there was omega 1, 2, and there was down here omega 3, 4. They'll be on the next slide. So let's deal with omega 1, 2 first. Okay, so I1 is 1, I2 is 2. All right, here we go. We can put that in there, epsilon 1, 2. We've got the 1 over 2 factorial from up here. Omega I1, I2, well, that's just A, remember here, that's just A, that goes in there. And it's only the J's now to specify. And this is where the Levi-Civita symbol will help us again. So the relevant terms involve epsilon 1, 2, 3, 4 equals 1. Now this is an even permutation. In fact, it's no change whatsoever. So by definition, it's plus 1. Since 1, 2, 3, 4 is an even permutation of 1, 2, 3, 4. Okay, so we've got 1, 2 here, x, y. The only thing we can have then is z and w. They're the only two. They're logical things going there. Remember with the Levi-Civita, if any two of these indices are the same, then epsilon is 0. For even permutations of 1, 2, 3, 4, we have 4 variables, x, y, z, w. Even permutations will give us a positive number, plus 1. Odd permutations of those numbers will give us minus 1. All right. So we have an even permutation, in fact, no change whatsoever. Thus, the only non-zero term comes from J1 equals 3, Z, J2 equals 4, W, and so the Hodge star of A dx wedge dy is A dz, okay, because dx3 wedge dx4, well, dx3 is just dz, dx4 is just dw. So we have A dz wedge dw. All right, let's keep going. All right, now for omega 3, 4 equals B, wedge the star, Hodge star of B dz wedge dw is 1 and 2 factorial, all this, epsilon 3, 4. Okay, so what can J1, J2 be? Remember, omega 3, 4 is B. So I'll get J1 and J2. Let's have a look. So the relevant terms involve epsilon 1, 2, 3, 4 equals minus 1. That should actually be, my apology, that should be epsilon 3, 4, 1, 2. Sorry about that. That should be flipped, and it's equal to minus 1. Since 3, 4, 1, 2 is an odd permutation of 1, 2, 3, 4. Okay, so my apologies, that should be epsilon 3, 4, 1, 2. I missed that in the vetting. My apologies. That's actually epsilon 3, 4, 1, 2 equals minus 1. Okay, that's the only non-zero term comes from J1 here equal to 1, J2 equal to 2. Okay, that goes in there. And that's an odd permutation, so minus 1. So the Hodge star of B dz wedge dw is minus B dx wedge dy. All right. Now, finally, the next step is to combine the results. So Hodge star of omega is A dz wedge dw from the previous slide minus B dx wedge dy from this slide. My apologies about this here. That should be epsilon 3, 4, 1, 2 equals minus 1. I can't stress that enough. I find these things and they annoy me. Anyway, unfortunately, I wish I could find them earlier. Anyway, let's move on. All right, so the Levi-Civita symbol definition, the Levi-Civita symbol, epsilon, with all those up there, we can have it lower down as well, is a completely anti-symmetric tensor defined on an n-dimensional manifold. It's used to express orientations and volumes in differential geometry. And for a given permutation of indices, I1 to ik, J1 to jnk, the following holds. All right. Can I just point out here, we can have the indices up and we can have them down. And the difference is the metric tensor, which is what we use to raise and lower. All right. There is a relationship for that. I was going to include in the video, I seem to have left it out. But anyway, epsilon, all that is equal to plus 1 if there are an even permutation of natural order, 1, 2 to n, and it's equal to minus 1 if they are an odd permutation, and it's equal to 0 if any two indices are the same. All right, so talking about 1, 2, 3, 4, all the way up to n, even permutation of those numbers will give you plus 1. An odd permutation of that order of numbers there, list of numbers there, will give you minus 1, and 0 if any two indices or more are the same. So for example, consider a two-form omega as dx wedge dy on R3. The Hodge star of omega using the Levi-Civita symbol is star dx wedge dy is epsilon 1, 2 z dz. Okay, because we know it's dz from the earlier example. Remember about 3 slides in earlier in the video. So what is this epsilon 1, 2 z? Well, here the Levi-Civita symbol epsilon 1, 2 z is plus 1 because 1, 2 z is an even permutation of 1, 2, 3 because the only other possibility we can have here is 3. We're in 3 dimensions. It's the only numeral that we could possibly use here. We can't have indices being the same, otherwise this would be 0. And the Hodge star there wouldn't be defined. What you have here, the only number that can go there is 3. All right, and that's an even permutation of 1, 2, 3. No change basically, so plus 1. All right, next thing is, in the next video we will look at several examples of its use. So this series carries on. There's one more video to go and we have some more to look at. Thank you very much for watching. Like I said again, thank you very much for watching this video. I hope you find it useful, and I will look forward to seeing you in the next video, the second part, and we will complete this short series here on the Hodge star operator. Okay, thank you very much. Take care, and I'll see you next time. All right, bye.